Look closely at the Kailasa Temple at Ellora. It is not built, it is carved. The largest monolithic structure on earth, it was excavated downwards and outwards from a single basalt cliff, demanding the removal of over 200,000 tons of rock. This achievement, executed by the Rashtrakuta dynasty, presents a structural paradox. The structure's monolithic nature is its greatest strength, yet its immense concentrated mass is simultaneously its chief vulnerability. For the master builders, stability was not a matter of mortar and stone, but of understanding the bedrock itself, the high-pressure interface between the monumental temple and the unstable geology beneath. This inquiry delves into how laboratory rock mechanics, specifically friction analysis, validates the temple's ancient structural design, especially the Gaja Pitha, or the elephant trees. Essentially, the temple is carved into Deccan basalt, a component of the Deccan traps, which possesses high durability but is highly heterogeneous. The critical issue lies not in the competent rock, but in the pervasive internal hairline faults inherent to the stratigraphy. The sequence of lava flows is interrupted by weak plains, weathered rock seams, and layers of fine-grained clay material known as bole. Geotechnical analysis confirms that these layers act as pre-existing failure planes, posing foundational problems of seepage and sliding. The immense gravity loads of the monolithic temple, the primary downward force, is concentrated directly onto these weak basal planes. Given the high compressive strength of competent basalt, which often exceeds 34.08 MPa, the immediate risk is not crushing, but rather shear failure, particularly if water infiltrates these clay-rich seams over centuries. This threat elevated the importance of frictional resistance at the base to an existential structural necessity. To understand how Kailasa remains standing, we must return to geotechnical engineering and the triaxial compression test. This laboratory procedure stimulates the exact stress rate at the temple's foundational interface. A cylindrical rock specimen, often containing a pre-cut joint or a natural fault, is subjected to a confining pressure from a hydraulic chamber, which is analogous to the later restraint provided by the surrounding mountain mass. An increasing axial load is then applied until shear failure occurs along the fault plane. This axial load is the experimental analog for the massive gravity load of the temple itself. By measuring the precise load required to induce sliding failure, engineers can determine the critical shear strength required for stability. The triaxial test is therefore a controlled and scalable model that validates the structural challenges faced by the original Rashtrakuta architects. So let's dive deep into the fault lines. The stability of the temple's base can be understood through a simple rule from rock mechanics called the Moore-Coulomb criterion, which describes how much pushing and sliding a surface can resist. In this case, the temple's rock acts like two surfaces pressed together, basically one trying to slide and the other resisting through stickiness or cohesion and roughness or friction. When water seeps into the clay layers within the basalt, it washes away the stickiness, leaving only the roughness to hold everything steady. The ancient architects therefore had to shape the temple's base so that its enormous weight pressed down evenly across the rock, increasing friction and keeping it locked in place. Basically, much like how a heavy wooden door stays firmly shut when its wedge is jammed tightly under it, using pressure and surface contact to prevent slipping. Heavy doors or not, let's address the elephant in the room, or the elephant underneath the temple. The resulting architectural necessity is manifested in the Gaja Pitha, the monumental elephant frieze positioned at the temple's base. While aesthetically magnificent, depicting elephants seemingly supporting the structure, its primary structural function is actually geotechnical. By carving the temple's plinth deeply into the bedrock and detailing it with complex, massive geometry, the builders fundamentally altered the friction characteristics of the contact interface. A flat contact surface over a weak seam is highly susceptible to sliding. However, the shear bulk and irregular interlocked form of the Gajathara geometry ensures that any potential shear failure plane would have to traverse a significantly increased and highly irregular surface area. This complex geometry creates mechanical interlock, acting as an engineered shear key. So, you see the temple's base. The Gajathara isn't just a platform. It's like the grip of a mountain-sized shoe holding the entire structure steady against gravity and earthquakes. Across India, temples like Modhara and Lingaraja used clever stonework. Each block cut so precisely that they lock together like puzzle pieces, using friction instead of glue or metal. This let them flex slightly during small tremors without breaking, just like how your knees bend to absorb a jump. So, shall we go from physics to Pitham? Having established the engineering necessity of the massive elephant's base, the narrative moves to its symbolic resonance. The Gaja Pitha directly invokes the concept of the Diggajas, or directional elephants, which are also sometimes called Din Naga. These 8 legendary elephants are cornerstones of Hindu cosmology, believed to serve as the guardians of the universe's zones and to physically uphold the 4 quarters of the world. They are the ultimate symbols of unshakable strength, cosmic balance, and stability. By depicting the temple as being physically borne by these entities, the architects achieved a profound convergence. The physical foundation required by geotechnical laws was simultaneously established as the metaphysical foundation required by cosmic law. The choice of the elephant was thus not merely decorative, it was a cosmological declaration that the structure's stability had been perfected, achieving permanence assured by the guardians of universal order. In the architectural language of the Rashtrakutas, the sheer force of gravity which activates the resistance to shear failure is visually represented as the burden willingly carried by the cosmic elephants. The ancient master builders did not just solve an engineering problem, they transcended it. They recognized that the empirical laws governing rock friction were merely the tangible, structural expression of the cosmological laws governing stability and order. Before you rush into giving credit to the aliens, let's try and understand how the Kailasa Temple is more than a religious monument. It is a textbook in applied geomechanics, very relevant to the human world. Our investigation traces a clear line from the lab bench where the triaxial apparatus models the friction angle of Deccan basalt, to the massive Gajathara plinth, which structurally maximizes this friction, and finally to the symbolic power of the Diggajas, who guarantee cosmic permanence. This structure stands as unparalleled proof that in ancient engineering, empirical foresight and profound cultural symbolism were unified, creating an immovable masterpiece where physics and philosophy are one.